Section: Introduction. In this section, we discuss generative adversarial networks, or GANs, which allow us to create high-quality images in a single forward pass. However, the original goal set by Goodfellow and colleagues is challenging to optimize due to its minimax nature. This creates concerns about stability, leading to the possibility of divergence, and it can also result in a lack of diversity in generated images, known as mode collapse. Despite advancements in GAN objectives, we still frequently encounter issues with unstable losses, which negatively affects GAN research. Additionally, many popular GAN architectures, like style GAN, rely on various empirical tricks that lack a solid theoretical foundation. For example, style GAN uses a specific loss function to enhance stability, which can impact sample diversity, and it also employs a technique involving mini-batch standard deviation to improve diversity. Without these tricks, style GAN resembles older models like DCGAN from 2015, yet it remains a common backbone for state-of-the-art GANs, such as GigaGAN and style GAN-T. Compared to other generative models, like diffusion models, GANs have seen slower progress. Modern techniques in computer vision, such as multi-headed self-attention and advanced architectures like pre-activated ResNet, UNet, and vision transformers, are now standard. Given the outdated architectures in GANs, it is understandable that many believe GANs do not perform well in terms of quantitative metrics like Frechet inception distance. We aim to address this situation by combining improved objectives with a regularized training loss, which enhances stability and allows us to incorporate modern architectures into GANs. We propose a new objective that enhances the relativistic pairing GAN loss with zero-centered gradient penalties to improve stability. We demonstrate mathematically that this gradient-penalized approach ensures local convergence, while removing our regularization leads to non-convergence. With a well-behaved loss function, we find that the traditional tricks used in GANs are unnecessary, enabling us to design a modern state-of-the-art backbone architecture. We simplify style GAN by identifying its essential features and integrating new designs from contemporary convolutional networks and transformers. Our findings indicate that proper ResNet design, initialization, and resampling, along with grouped convolution and no normalization, are crucial. This results in a simpler design than style GAN, which improves FID performance for the same network capacity. In summary, we argue that GANs can be trained effectively without complex tricks by using an improved regularized loss. We also empirically develop a straightforward GAN backbone that, without any tricks, performs favorably in terms of FID compared to style GAN, other state-of-the-art GANs, and diffusion models across various datasets. We also address two main challenges in defining a GAN objective: stability and diversity. Previous research has focused on either stability or mode collapse, but we combine a stable method with a simple, theoretically grounded regularizer to make progress on both fronts. A traditional GAN is set up as a minimax game between a discriminator and a generator. The generator aims to minimize a loss function while the discriminator seeks to maximize it. The choice of the loss function is flexible, and we adopt a specific one that has been shown to have convex properties when the generator's output can be optimized directly. However, in practice, the empirical GAN loss often shifts fake samples beyond the decision boundaries set by the discriminator, complicating the optimization process and leading to issues like mode collapse and non-convergence. To tackle mode collapse, we utilize a slightly different approach called the relativistic pairing GAN. This method evaluates the difference between real and fake data in a way that prevents the generator from simply pushing fake samples past a single decision boundary, which is a common cause of mode collapse. By coupling real and fake data, we create a more robust decision boundary that helps avoid these pitfalls, ensuring that every local minimum corresponds to a global optimum. Section Summary. In this section, we discuss the challenges of stability and diversity in GANs, highlighting the difficulties in optimizing traditional objectives and the reliance on empirical tricks in popular architectures like style GAN. We propose a novel regularized loss for GANs that enhances stability and allows for the use of modern backbone architectures, demonstrating improved performance without the need for complex tricks. Section: Training Dynamics of RPGAN. In this section, we examine the training dynamics of RPGAN. While the landscape of RPGAN helps us tackle mode dropping, we still need to investigate its training dynamics. Our main objective is to find the equilibrium points where the distribution generated by RPGAN matches the real distribution, and the discriminator remains constant across this real distribution. Previous work indicates that these equilibrium points can be reached along a specific path, but this doesn't guarantee that gradient descent will find them. We confirm that unregularized RPGAN may not converge using gradient descent, especially for certain types of real distributions, like those that resemble a delta function. Therefore, we need additional regularization to ensure a well-behaved loss function. To address the non-convergence of RPGAN, we explore gradient penalties, specifically zero-centered gradient penalties, 0GP, which have been shown to help classic GANs converge. The two main types of 0GPs we consider are R1 and R2. R1 penalizes the gradient of the discriminator on real data, while R2 does so on fake data. Most analyses of GAN training dynamics have focused on local convergence, meaning whether the training converges when the parameters are close to the equilibrium points. We analyze the behavior of the gradient vector field at these points and find that when the generator produces the true distribution, we want the gradient of the discriminator to be 0 to prevent oscillation. Both R1 and R2 help achieve this when the generated distribution matches the real one. We also note that previous gradient penalty methods, like the one-centered gradient penalty used in WGAN-GP, fail to ensure convergence because they still allow the discriminator to have a non-zero slope when the generator is optimal. We extend our analysis and show that RPGAN with R1 or R2 regularization can converge locally under similar assumptions as previous studies. Our proof demonstrates that the eigenvalues of the Jacobian of the regularized RPGAN gradient vector field have negative real parts, indicating convergence near the equilibrium points for small learning rates. In our discussion, we connect R1 and R2 to noise stability, as shown in earlier work. We find that R1 approximates the convolution of the real distribution with a normal distribution, while R2 does the same for the generated distribution. The error terms from R1 and R2 cancel out when the discriminator approaches its optimal state. Although we do not extend this proof to RPGAN, it may provide additional insights into our findings. For practical demonstration, we test our loss function on stacked MNIST, which has 1,000 uniformly distributed modes. We use a small ResNet for both the generator and discriminator without normalization layers. By employing a pre-trained MNIST classifier, we can measure how many modes of the real distribution are captured by the generated distribution. We also estimate the reverse KL divergence between the generated and real samples. Our experiments show that a conventional GAN loss with R1 diverges quickly. Similarly, while RPGAN with only R1 is theoretically sufficient for local convergence, it is also unstable and diverges rapidly. However, when we apply both R1 and R2, the training stabilizes for both classic GANs and RPGAN. We observe that while classic GANs suffer from mode dropping, RPGAN achieves full mode coverage and significantly reduces the KL divergence. We find that R1 alone is not enough for globally convergent training. Although analyzing this theoretically is challenging, our experiments suggest that early in training, the parameters are unlikely to be close to the equilibrium points. If the discriminator is powerful enough, regularizing it only on real data may not effectively influence its behavior on fake data, leading to training failures. Previous studies have noted that regularizing the discriminator with only R1 can cause gradient explosions on fake data due to memorization of real samples. Thus, we conclude that regularizing the discriminator on both real and fake data is essential. We also find that applying both R1 and R2 smooths the learning process for both the real and generated distributions, making it easier than just smoothing the real distribution. Our empirical results indicate that with both regularization terms, The discriminator maintains a balanced gradient norm on real and fake data, which helps prevent overfitting. Section Summary. In this section, we analyze the training dynamics of RPGAN, highlighting that unregularized versions may not converge using gradient descent, particularly for certain distributions. We demonstrate that incorporating both zero-centered gradient penalties, R_1 and R_2, stabilizes the training and improves mode coverage, addressing issues of mode dropping and ensuring local convergence near the optimal parameters. Section. A roadmap to a new baseline, R3GAN. In this section, we outline our approach to developing a new baseline model called R3GAN. We start with a well-structured loss function that helps address optimization issues in GANs, allowing us to create a minimalist baseline using recent advancements in network architecture. Instead of merely presenting our new method, we will trace our development from the style GAN2 model. Our initial model, referred to as config-A, utilizes a VGG-like backbone for the generator and a ResNet for the discriminator, along with several techniques that enhance style-based image generation and various adjustments to improve the model's performance. We then simplify this by removing unnecessary features in config-B, applying our loss function in config-C, and gradually modernizing the network architecture in config-D and E. We evaluate each configuration using the FFHQ dataset at a resolution of 256 by 256 pixels, maintaining a similar network capacity across all configurations, with both the generator and discriminator having around 25 million trainable parameters. Each configuration is trained until the discriminator processes 5 million real images. We inherit training hyperparameters from config-A unless stated otherwise and fine-tune them for our final model. In config-B, we eliminate all features from style GAN2, retaining only the core network backbone and basic image generation capabilities. The features we focus on fall into three categories: style-based generation techniques, image manipulation enhancements, and various tricks to improve performance. We reduce the dimensionality of the input to 64, which requires us to lower the learning rate significantly. Although this simplified baseline has a higher FID score compared to config-A, it still produces acceptable sample quality and stable training. We compare our results with DCGAN, an earlier image generation model, noting key differences such as our use of a convergent training objective with regularization, a smaller learning rate, and the absence of normalization layers in both the generator and discriminator. We also ensure proper resampling through bilinear interpolation instead of using strided convolutions. For activation functions, we find that smooth approximations of ReLU tend to worsen performance, so we stick with leaky ReLU. All subsequent configurations follow the principles established in our earlier work. In config-C, we implement our proposed loss function, which reduces the FID score further. We suspect that the backbone architecture from config-B is a limiting factor. Moving to config-D, we adopt a 1-3-1 bottleneck ResNet architecture for both the generator and discriminator, incorporating beneficial principles from our previous configurations and modernization efforts from Convenext. We categorize these principles into three groups: consistently beneficial changes, negligible performance gains, and those irrelevant to our setup. We aim to apply the beneficial changes to our model while reserving others for future configurations. Overall, we focus on optimizing our model while avoiding normalization layers, as previous findings suggest they can hinder performance. We also choose not to adopt certain design choices from Convenext that do not yield significant improvements. Section Summary. In this section, we outline the development of R3GAN, a minimalist baseline model that simplifies style GAN2 by removing non-essential features and modernizing the network backbone while maintaining similar capacity. We evaluate various configurations, demonstrating that our well-behaved loss function and architectural adjustments lead to improved sample quality and training stability, despite some trade-offs in performance metrics. Section. Neural Network Architecture Details. In this section, we detail our neural network architecture. We replace the style GAN2 backbone with an updated ResNet, using a fully symmetric design for both the generator and discriminator, each having 25 million parameters, similar to config A. Our architecture is minimalist, with each resolution stage featuring one transition layer and two residual blocks. The transition layer includes bilinear resampling and an optional 1x1 convolution to adjust spatial size and feature map channels. Each residual block consists of 5 operations: a 1x1 convolution followed by a leaky ReLU activation, a 3x3 convolution, another leaky ReLU, and a final 1x1 convolution, with the last 1x1 convolution not including a bias term. At the 4x4 resolution stage, we substitute the transition layer with a basis layer for the generator and a classifier head for the discriminator. The basis layer, akin to style GAN, utilizes 4x4 learnable feature maps modulated by a learned layer. The classifier head employs a global 4x4 depthwise convolution to eliminate spatial dimensions, followed by a learned layer to generate the discriminator's output. We maintain the width ratio for each resolution stage as in config A, making the stem width 3 times wider due to the efficient 1x1 convolution. The 3x3 convolution in the residual block has a compression ratio of 4, resulting in a bottleneck width that is 0.75 times that of config A. To prevent variance issues from the lack of normalization, we use fix-up initialization. We initialize the last convolutional layer of each residual block to 0 and scale down the initialization of the other 2 convolutional layers by the 4th root of the number of residual blocks. We avoid additional fix-up techniques, such as excessive bias terms and a learned multiplier. Next, we explore modernizing the residual block. We replace the 3x3 convolution in the residual block with a grouped convolution, setting the group size to 16. This change allows us to reduce the bottleneck compression ratio to 2 while keeping the model size the same, increasing the bottleneck width to 1.5 times that of config A. We find that the computational cost of grouped convolution is minimal compared to 1x1 convolution, so we aim to enhance its capacity. We invert the bottleneck and stem widths, effectively doubling the width of the grouped convolutions without increasing the model size. In our experiments, we analyze the performance on FFHQ 256. Config A, which uses the standard style GAN2, achieves an FID score of 7.52. Config B, with all enhancements removed, results in an FID of 12.46, as expected. Config C, which has a well-behaved loss, achieves an FID of 11.65, indicating stability for architectural improvements. Config D, which enhances both the generator and discriminator based on classic ResNet and convenext principles, achieves an FID of 9.95. We find that the output skips from the style GAN2 generator are not beneficial in our new architecture, leading to a worse FID of 10.17 when included. We note that previous work suggested a ResNet architecture could be detrimental to the generator, but our implementation differs significantly. For config E, we conduct 2 experiments to assess the impact of increasing width with depthwise convolution and inverting the bottleneck. By adding grouped convolution and reducing the bottleneck compression ratio to 2, we achieve a bottleneck width that is 1.5 times that of config A, resulting in an FID of 7.51, surpassing style GAN2. By inverting the dimensions to enhance grouped convolution capacity, our final model achieves an FID of 7.05, exceeding the performance of style GAN2. Section Summary. In this section, we detail our modernized neural network architecture, replacing the style GAN2 backbone with a symmetric ResNet design that includes 25 million parameters for both the generator and discriminator. We implement a minimalist structure with specific convolutional layers and enhancements, achieving improved performance metrics, as evidenced by a drop in FID scores, surpassing the original style GAN2 results. Section. Mode Recovery. Stacked MNIST, 532016 Metz et al., Metz, Poole, Thau, and Sohl-Dickstein. In this section, we repeat our earlier experiment on mode convergence using stacked MNIST, this time with our updated architecture and comparisons to state-of-the-art GANs and likelihood-based methods. We note that likelihood-based models, like diffusion, tend to cover more modes than GANs, which often struggle with this. However, our approach, along with PRES-GAN and DD-GAN, successfully captures all modes and shows better performance in terms of KL divergence. Next, we train our model on FFHQ at a resolution of 256 by 256 with optimized hyperparameters and training schedules. Our results indicate that we outperform existing style GAN methods and 4 recent diffusion-based methods. Notably, many other methods use a trick called BCR, which has only been shown to enhance performance on FFHQ 256, but we do not employ this trick. We also evaluate our model on FFHQ at a lower resolution of 64 by 64 to compare directly with EDM. By removing the 2 highest resolution stages from our 256 by 256 model, we create a generator with fewer than half the parameters of EDM. Despite this reduction, our model still outperforms EDM and requires only 1 function evaluation. For CIFAR10, we train our model until convergence with optimized hyperparameters. Our method achieves a better FID score than many other GANs, even with a smaller model capacity. For instance, while Style GAN XL has 18 million parameters for the generator and 125 million for the discriminator, our model combines to only 40 million parameters. Additionally, our GAN approach is significantly more efficient than diffusion models, needing just 1 evaluation compared to the many required by diffusion models. We also compare our model on ImageNet 32, adjusting our generator to match the size of Style GAN XL's generator. Our method achieves a comparable FID score despite using a 60% smaller discriminator and not relying on a pre-trained ImageNet classifier. Finally, we test our model on ImageNet 64 to assess scalability. By adding another resolution stage to our ImageNet 32 model, we create a generator with 104 million parameters, which is nearly 3 times smaller than diffusion models that use the Admiral backbone. Despite this smaller size and generating samples in 1 step, our model still outperforms larger diffusion models in terms of FID. Section Summary. In this section, we demonstrate that our updated architecture successfully achieves mode coverage on stacked MNIST and outperforms state-of-the-art GANs and diffusion models across various datasets, including FFHQ and CIFAR10, while requiring significantly fewer function evaluations. Our model also maintains competitive performance on FID metrics without relying on pre-trained ImageNet classifiers, showcasing its efficiency and effectiveness. Section Recall. In this section, we evaluate the recall of our model across different datasets to measure sample diversity. Overall, our model's recall is comparable to, or slightly worse than, the diffusion model, but it outperforms existing GAN models. For CIFAR10, our model reached a recall of 0.57, while Style GAN XL had a lower recall of 0.47, despite its better FID score. For FFHQ, we achieved a recall of 0.53 at a resolution of 64 by 64 and 0.49 at 256 by 256, whereas Style GAN 2 had a recall of 0.43 at the higher resolution. Our ImageNet 32 model achieved a recall of 0.63, which is similar to ADM, and our ImageNet 64 model reached a recall of 0.59. Although this is slightly lower than the approximately 0.63 that many diffusion models achieve, it is still better than Big GAN Deep's recall of 0.48. In our discussion, we demonstrate that we can simplify GANs for image generation tasks using a more stable RPGAN with specific convergence properties, which still yields diverse outputs. This stability allows us to redesign a modern network architecture without relying on previous methods, resulting in the R3 GAN model, which shows competitive FID scores on common datasets like stacked MNIST, FFHQ, CIFAR10, and ImageNet. Our focus is on identifying the essential components of a minimal GAN for image generation, prioritizing simplicity over performance. We do not claim to outperform every existing model on all datasets. Instead, we aim to provide a straightforward baseline that converges easily. However, this simplicity means our model may not be suitable for direct application in downstream tasks like image editing or controllable generation, as it lacks specific features for easy image manipulation or disentangled synthesis. For example, we removed style injection from style GAN, despite its clear benefits, and we did not include techniques known to improve FID significantly, such as adaptive normalization or multi-headed self-attention at lower resolutions. We plan to explore these techniques in future studies. Additionally, our work is limited in its evaluation of the scalability of R3 GAN models. While they show promising results at 64 by 64 resolution for ImageNet, we have yet to test their scalability on higher resolutions or large-scale text-to-image generation tasks. Finally, we acknowledge that while our method can enhance the quality of generative models, especially those that create images of people, can pose risks, such as personalized deep fakes and the spread of misinformation through fake influencers.